All right, today we're going to talk about 2 by 2 determinants. So let's start with a matrix right now, A, B, C, D. And let's say we want to compute the inverse of that matrix. I said determinants, now you're doing inverses. Well, the inverse has a formula that tells you that it's going to be of the form 1 over AD minus BC times, then you're going to swap the diagonal entries, and you're going to throw negatives in the to the off diagonals. And if you multiply this matrix that I call the inverse on either side, remember multiplication is not commutative, times the matrix A, B, C, D, you'll get the identity. So if you would call this matrix that I wrote here as A, and this is called A inverse, you get that A times A inverse is equal to A inverse A, and that is going to be equal to the identity. All right, so this quantity down here is actually pretty important, because notice the importance of this quantity lies on the fact that if AD minus BC is equal to 0, then this matrix A inverse cannot be defined in such way. So let's say that A inverse does not exist. In other words, if AD minus BC is equal to 0, your matrix A, in this case ABCD, is non-invertible. Now, on the other hand, if that quantity AD minus BC is not equal to 0, whatever quantity you get, A inverse is well defined. So you could say that that quantity AD minus BC determines whether the matrix A is invertible. So we're going to say that the determinant of the matrix A, when A is the matrix I wrote there, 2 by 2 matrix, is going to be given by AD minus BC. So for 2 by 2 matrices, it's very easy, because if you have the matrix A being, you can say 1, 2, 3, let's not do 4, -3, just to have some variety, and you're going to compute the determinant. All you do is put all the quantities in the right order. AD is going to give you 1 times -3 minus BC is going to give you 3 times 2. And that's going to give you -9. So -3 minus 6, -9. And so that would be the determinant of this matrix. So the matrix I wrote here is invertible, and you can write the inverse by using that formula. Let's do that real quick. So this is going to be called the shortcut formula for us. So -1/9, I just did 1 over -9. I put the negative outside. Swap the diagonal entries, -3, 1. Throw negatives in front of the off diagonals. And if you wanted, you could distribute that -1/9, although it's not necessary. Often we will not do that, just due to the fact that it'll be, we can deal with a constant at the very end. But right now we're going to distribute it in. And so we get -1/9 times -3 is going to be 1/3. Same for this entry. Now this is going to be -2 times -1/9 is going to be 2/9. Whatever I wrote, not what I said. And then -1 times 1 is -1/9. And that right there gives you your inverse for that matrix. So the question is, how do we go up to 3 by 3? I'm going to erase this, and I'm going to come back and we're going to talk about that. All right, so now for 3 by 3, I can give you an explanation as to how or why we would define the determinant in the way that we'll do it. But that takes a long time, and I do it in class. If you're interested in seeing the motivation for it, let's put it in the comments, and I may get motivated to do the explanation on a video. But right now, let's say we have the matrix, the 3 by 3 matrix, and now let's start with A11, A12, A13, A21, A22, A23, and then A31, A32, and A33. So with that matrix A, let's define the determinant of the matrix. So the determinant of A, technically, we would define it just based on the first row. But as it turns out, this determinant is a combinatorial object, and you can expand it around or about first, second, third, whichever row you want. And I'm going to show you how you do it for 4x4 and or larger matrices in the next video. But in this video, I'm going to restrict myself to 3x3, because for 3x3 matrices, there's still some tricks that you can do. You may know about them already. But the determinant will be, you're going to fix one row. So let's do the row I. So you're going to grab A, I1, and you're going to multiply it times the cofactor A, I1. And I'm going to tell you what that is in a second. Then you do A1, I3, from 1 to 3. He doesn't know how to count. Oh well, you can count on that. So let me fix it, sorry. 2, A1, 2, and then we're going to do AI3, AI3. Alright, so what are these AIs? Well, AI1 is going to be the matrix that you obtain by eliminating. Oh, I gotta tell you, who am I eliminating? Well, AI1 is going to be your -1 times I plus 1 times the determinant of the submatrix that you obtain by eliminating the ith row and ith column. So, sorry, ith row and first column. A sub I 1, where the matrix AI1 represents the matrix A with the ith row and first column omitted. Let me change markers because this one is doing a little bit too much squeaking. So with that, we can also do a I2 to be -1 I plus 2, and then the determinant of that A tilde I2, where A tilde I2 would be the matrix with the ith row and second column omitted or deleted. So let's do an example how this formula works. So we're going to do the matrix A, which is going to be 1, 2, 1, 0, 1, 3, 3, -1, 2, whatever. So first step you're going to do, this is called the cofactor expansion. If you're going to do the cofactor expansion, choose a row that has the most zeros. Excuse me. Why would you do that? Well, because if you use your formula, then the determinant of A is going to be equal to the first entry, 0, times the determinant of that matrix A tilde sub, my row is 2, I'm picking the second row, and the first column. Okay. Do I care what number that gives me? No, because it's multiplied times 0, so I don't have to compute it. That's why you choose however many zeros you can. Then 1 times -1. Ooh, it's true that you're multiplied times 0, but somebody forgot this term here. So since I'm multiplying times 0, I'm going to omit it, but technically you have to have a -1 to the 2 plus 1, which is going to be a negative term here. Now this next one is going to be -1 to the power of 2 plus 2, determinant of A sub 2 tilde. That's going to be the matrix where you eliminate the second row and second column. Lastly, you're going to pick the next entry. By the way, I should have been labeling things or coloring things around. This 0 is this 0, this 1 is this 1, and then I'm using the formula for each one of those entries. Now, the next one, apparently I needed to hit shift to make this a plus, not an equal. 3 times the negative 1 to the power of 3 plus 2, or 2 plus 3 in the order I wrote it, determinant of a tilde 2, 3. Alright, so that's just filling in the formula. And of course this looks complicated, but it's really not. We'll talk about how to simplify it here in a minute. So what that then becomes is going to be 0 times determinant of a to 1. That's 0. I'm not going to write it. Now I get negative 1 to the power of 2 plus 2. That's going to be 1. 1 times the determinant of the matrix a to 2. So how do I make a to 2? I'm going to eliminate or a to 2 tilde. I'm going to eliminate the second column and second row, and I'm going to write the matrix that I obtain. The matrix that I obtain is going to be 1, 1, 3, 2. Those are the terms that survive. And now here I'm going to do plus, it's going to be minus 3 times negative 1 to the power of 5. Negative 1 to the power of 5 is negative, so I'm going to write negative 3 times the determinant of a to 3. A to 3 is going to be the matrix that I obtain by eliminating the second row and third column. So basically, whenever you grab a coefficient, you put that coefficient and then you eliminate that row and column. So let me try to eliminate this. It's not going to work out, but at least so you can see it a little bit more faint. I'm going to get the matrix that survives, which is going to be 1, 2, 3, negative 1. So eliminating for second row and third column. So 1, 2, 3, negative 1. But you see, the beauty of this formula is that it's a recursive formula. Notice that when I eliminate a row and a column, I drop the size of a matrix by 1. So I had a 3 by 3, now I have a 2 by 2. And 2 by 2 I do know how to do because we just talked about that formula before. So all I do is use my formula. And so here I get 1 times, so I don't have to write that. 1 times 2, 2 minus, and I should have told you who 1 and 2, where they're coming from, diagonals minus off diagonals. So 1 times 2 minus 3 times 1. So 2 minus 3. Now here I get minus 3 times, and then I get 1 times negative 1 minus 3 times 2. 3 times 2, 6. So I get this number, which is going to be negative 1 minus or plus 3 times 7, which is going to be 21 plus minus 1, 20. So the determinant of that matrix right there will be 20. So let's compute that determinant in a different way. Alright, so noticing that the video is a little bit long, I'm going to do a continuation for this video where we're going to talk about shortcut methods for 3 by 3 matrix. I'm going to show you how to do 4 by 4. And then I'm going to show you a way to use row operations to compute larger determinants in an easier way. So thank you for watching, and I'll see you in the next one.